Hi everyone, my name is Miguel. I am a PhD student at the Center for Physics of the University of Porto, and I'm here to tell you about our work that has recently been published in Physical Review D called Cosmological and Lunar Laser Ranging Constraints on Evolving Dark Energy in a Non-Minimally Coupled Curvature Matter Gravity Model. If you want, you can find more details in the publication online or on the archive preprint if you so wish. Dynamical dark energy has been all the rage lately. The DESI collaboration shared hints that we might have potential deviations from a cosmological constant. So the equation of state parameter of dark energy may not be a constant equal to -1. It may actually evolve over time, and in fact, even have a phantom crossing at low redshifts. This is also shown in terms of the CPL parameterization, in terms of WA and W0, where GR will be recovered at this crosshair right here, and we're seeing over 2 sigma deviation when combining DESI, CMB, and also some different supernova data, that we are seeing evidence of over 2 sigma from deviations of GR. The model that we are looking at is going to try to explain these kinds of deviations. The model is the non-minimally coupled F of R model. It effectively comes as an extension of the minimally coupled F of R model shown here as this function F1, and with the addition of this function F2 multiplying the matter Lagrangian. GR will be recovered if we set F1 equal to the curvature scalar minus twice the cosmological constant, where the cosmological constant here is being inserted directly into the gravitational part of the action, while F2 here is modeling our nonminimal coupling. And so if it is 0, we have GR because GR is minimally coupled. Our model is going to have the minimal part exactly the same, so we still have a cosmological constant in there, but we have a non-minimal part that is a power law function of the Ricci scalar with a coupling mu and an exponent m that is going to create this dynamical dark energy behavior over the cosmological constant. Because of the Lagrangian showing up multiplied by a function of the Ricci scalar, it means that it will show up explicitly in both the field equations and the conservation equations. That does not happen in GR, where only its variation shows up. And so here we've got two choices for the perfect fluid Lagrangian, which will no longer be equivalent. The first one is the matter Lagrangian being equal to minus the density. This is the most common choice. It has been researched in the context of the Hubble tension, inflation, and gravitational waves, among others. It recovers the standard conservation equation. So here I'm showing the standard conservation equation you have in GR, which is exactly the same thing you have been taught in undergraduate courses. And then it can also contribute significantly at late times because the modifications are going to be proportional to the matter Lagrangian. And because the matter density of the universe is around a third of the content of the universe at present, it means that we can still have some considerable modifications. If we look at the other option, equal to the pressure, then this does modify the conservation equation. Our conservation equation is now going to look like the GR conservation equation with an extra term, which is effectively going to be reflected as an additional coefficient in rho that is going to evolve over time apart from the typical evolution we have in GR. However, this has little effect on the field equations at late times because the pressure is so small at late times. The pressure is going to be quite small because we are in a matter-dominated universe in terms of the actual matter content, not including the cosmological constant, and the pressure of that is so small that effectively we're going to be forced to recover GR. So we're going to keep the Lagrangian equal to minus rho and stick with it throughout our whole work. We also have to obey some physical constraints for the consistency of our model. The first one is that our model needs to be late time dominant. That means that we do not expect our model, we don't want our model to affect the observed features of the cosmic microwave background. That has to do with the fact that they are so precisely measured. And we know the curvature grows into the past as the universe is contracting into the past or expanding into the future. And so any noticeable late time effects, if they then increase into the past, are going to be absolutely huge. And so they can completely spoil the CMB data. So we must have a non-minimal coupling that decreases with the curvature. And that means that we need to have F2 have a negative derivative in respect to the Ricci scalar. And that imposes that our exponent m needs to be negative. The second condition is the stability of the model. So the model should be stable at the perturbative level. That means ensuring that the mass squared of the induced degree of freedom of the theory must be positive. This induced degree of freedom has a mass squared that is proportional to the second derivatives of F1 and F2 with respect to the Ricci scalar. And it turns out that in our model under consideration, this is proportional to mu, m, and rho. Because of rho being positive and m being negative, as we just saw, this means that for the stability of the model, mu must necessarily be negative, or else we can run into Dolgov-Kawasaki instabilities because of the mass square being negative. The field equations are represented in terms of a scalar field that we define here in terms of the first derivatives of both f1 and f2. Because f1 is just r plus a constant, it is going to just be 1, while this derivative is going to have dynamical behavior to it. And in GR, this eta scalar field will be a constant scalar field, so a non-dynamical scalar field equal to just 1. So it recovers GR when eta is equal to 1. The trace of the field equations gives us a wave-like equation for these scalar fields in terms of an effective potential, whose derivative in respect to the scalar field itself we show here. That's why the scalar field representation is so useful, because it allows us to represent this via a wave equation which we understand quite well. The effective potential itself is going to have critical points when this derivative of the potential is equal to 0, which gives us an equation in terms of the Ricci scalar, the exponent, the coupling, rho, and the cosmological constant, which we can write equivalently as this function g of r, which is the left side of the equation, equal to a constant equal to b, which is rho plus 4 lambda. This has three options. We either get the minimum of this function g of r being greater than b, in which case we have no minimum of the effective potential. We can have the minimum value of g equal to b, in which case we only have one critical point, which turns out to be an inflection point of the effective potential. Or we can have the minimum value of g less than b, in which case we're going to have one minimum and one maximum of the effective potential. The reason why this is the case is because if we look at the function g of r, in this specific case where the g min is below the threshold b, the asymptotic behavior of the function, where it grows infinite at small r and it goes linearly at large r, means that it's going to cross the value of b twice, and therefore we're going to have two critical points. It turns out that if they exist, these two critical points consist of a maximum, eta 1, and a minimum, eta 2, which is always greater than eta 1 in terms of its value of the scalar field, with the potential being given by this expression right here. The constant in terms of the density is irrelevant in terms of finding this minimum specifically, because it just shifts in terms of the density. Here we are showing time, the potential, effective potential in terms of the scalar field eta. We show the existence of a maximum over here, the existence of a minimum over here at larger values of eta near 1, where we would have GR, and we are showing it for different values of the density. So the density grows as this color goes from blue to red, which means we're going into the past. So if the color goes from red to blue, we are increasing in time, we are decreasing our density, and we are shifting our minimum through these curves from the red to the blue minimum. This shows up in the context of the tracking solution. The tracking solution has already been researched in works by Bragg and Faulkner in 2004 and 2007, where they show that you can have a solution that tracks the minimum of the potential, of the effective potential over time. And in this case, our field is going to track this exact minimum. The requirement for this to be true is that the period of oscillations around this minimum, which is given by the inverse of the second derivative of the potential at this minimum, the period needs to be very small with respect to the expansion rate. So effectively, we're saying that these oscillations are so fast that it is effectively as if the field was exactly at the minimum as the potential is progressing. The potential evolves, the minimum is oscillating so fast that it is effectively always at the minimum of the potential. This gives us two conditions for our solution. The first one is the existence of a minimum of the effective potential, as we talked about before. This comes in the shape of a bound on mu in terms of the exponent m and the cosmological constant lambda. We also need to impose the validity of the tracking solution, which is shown here as a constraint on mu, also on given in terms of r naught, which is given by the matter density at present, the exponent m, and this function v, epsilon. Now, epsilon is a small number. We can make it as small as we want. That will just make our constraints tighter and tighter and tighter for the tracking condition. And then this function v depends on the value of chi, where chi is the ratio of 4 lambda to rho, effectively telling us how much dynamical behavior there is in the universe. Lambda is not dynamical itself. Rho is dynamical. And so the more lambda there is, the less rho there is in comparison, and therefore we are going to have chi being quite big, and in general that's going to have an effect of having or reducing the effects of the model. We show here on the right plot the conditions for each one. The tracking condition, it turns out, is always stronger than the condition for the existence of the minimum, and therefore it is enough for us to consider the tracking condition to ensure that any model is physically consistent whenever we're doing our analysis later on. In terms of the dynamical dark energy behavior, this comes about because we recast the Friedmann equation in terms of the matter density, as usual, and then the cosmological constant with some dressing from the non-minimal coupling. The non-minimal coupling here is going to induce a time-dependent, here scale factor dependent contribution, also depending on chi, that ratio of the cosmological constant to the matter density I showed before, and also xi, where xi is going to model the contribution of the model to gr. Now, gr would just be eta equal to 1, and therefore xi equal to 0. So the larger xi is, the further away we are from gr. In the plot on the right, I show how xi varies for different values of rho. So at very large rhos, which are the very early past, we are going to get xi going to 0, and therefore we recover lambda CDM in the very far past. Similarly, if we go into very small values of rho comparatively to the rho we have today, we recover again lambda CDM because xi goes to 0. So in the far future, we recover lambda CDM. But around the present, when rho is comparable to rho naught, it turns out that we get xi being maximum, even if it is still small, and that means that that is where our dynamical dark energy behavior is going to show up, which is precisely what the data is suggesting. These numerator and denominator themselves are going to be functions, a series of this function 1 plus chi a cubed, which evolves over time, but also of xi itself. And so the smaller xi is, the easier it will be for us to recover the behavior of the cosmological constant. The cosmological constraints that we get are based on the following two data sets. The first one being supernova data from the Dark Energy Survey or from Pantheon. We never use them together, only separately, and we show both. These are catalogs of distance moduli of the type 1a supernovae, which we can also calculate theoretically using the luminosity distance, which depends on the background expansion rate h of z, which is modified in a non-minimal coupled model. We always marginalize over h naught because we are looking for dynamical dark energy, and dynamical dark energy does not really care about what h naught is going to be. And also for the case of the Dark Energy Survey DES, it turns out that h naught cannot be constrained specifically because there is a degeneracy there with distance moduli. Even though we can break it for Pantheon, we follow the same behavior of not breaking it in the same way that for DES we cannot break it in the first place. For DESI, we get BAO data, which are the ones that actually indicate some dynamical dark energy behavior. These come in the form of the ratio D over RD, where these capital Ds are these distances that are given in terms of the background expansion of the universe. So again, they will have the information about the late time modifications of the model. While we also get the sound horizon in this ratio, where the sound horizon is fully calculated from the redshift of decoupling onwards, the baryon photon decoupling onwards, which means that we have very, very early time effects, and our model recovers on the CDM at early times, and therefore we can keep RD the same as we would get from CMB data, which is around 147.46 megaparsec. These are the cosmological constraints we get. On the left, I'm showing the Pantheon Plus results, and on the right, I'm showing the Dark Energy Survey results, both of which are combined with DESI results. It turns out they are quite similar to each other, and so analyzing just one of them is enough to find out the whole picture. Looking at the Dark Energy Survey results, which are a little more stringent, we constrain the NMC curvature scale here on the bottom right plot of this corner plot, and we see that the best fit mu differs by over 1 sigma from GR, which would be mu equal to 0. And so our model, even though it includes GR as a limiting case, which would be mu equal to 0, does not recover GR statistically speaking. So it is over 1 sigma deviation from GR. For the specific case of m equal to -4, or its magnitude equal to 4, we find that the maximum value of xi occurs at around z of 0.35, or redshifts that are quite near the present, and it peaks at a value of 10 to the -3, give or take. And that is much smaller than 1, which is effectively what we would expect if the tracking solution is to hold, and so we don't have huge deviations from GR, but enough deviations that we can get some dynamical dark energy behavior. The Akaike and Bayesian information criteria, respectively, AIC and BIC, indicate weak preference for the non-minimal couple model and for lambda CDM, respectively, for each one. This difference stems from the fact that the BIC is more punishing of having extra degrees of freedom, while the AIC is not as much. Well, we have one more degree of freedom here, which is this coupling strength, and that is what's being punished here by the BIC. But effectively, these are saying that, all in all, these two models are almost statistically equivalent, while our model does reproduce dynamical dark energy, while lambda CDM is not able to. all the non-minimal couple models that we tested give omega m, so the matter density around 0.31, and h naught of around 68 kilometers per second per megaparsec, both of which are within 1 sigma of the DESI results, which is not surprising because we are using the same data and this model is not significantly modifying GR, but it is still good that we have that consistency there. We then look at dynamical dark energy itself. So the equation of state parameter can also be calculated theoretically using the parameters that we were using before, like chi and xi. We noticed that the dark energy survey results are more stringent than the Pantheon results that we show over here on the bottom, with the dark energy results having smaller areas of confidence. And both models, all models in both cases, exhibit a phantom crossing. So we always get the phantom crossing that is uniquely fixed by the value of m for each one. That is crossing over here, and the stronger coupling we get, the earlier the crossing is. That's why for lower magnitudes of m, there, for example, m equals -3, we cross earlier because we have a stronger coupling preferred by the cosmological data. You can also have a second crossing near the present, so a little before, a little after the present, which is something that is unique to this model, and then of course the CPL parameterization can never reproduce because it is a linear evolution of the cosmological equation of state for dark energy. We hope that future surveys may be able to constrain lower redshifts and therefore give us a better idea if such a second phantom crossing could occur. It is right now still allowed by the statistical significance of the data, but it could be that in the future it is either ruled out or ruled in. We then looked at comparison with lunar laser ranging constraints. This has to do with the fact that the non-minimal coupling creates a fifth force that makes the Earth and the Moon fall towards the Sun in the solar system with different accelerations, which is effectively a violation of the universality of freefall and can be constrained in terms of the effective masses of both the Sun, the Moon, and the Earth. And that is going to be constrained by 48 years of lunar laser ranging data, which is at the 3 sigma level around the order of 10 to the minus 14, which is quite stringent. And that translates to an upper bound on the coupling of the model, which we show here via this black line from an earlier work by March et al. In 2024. This shows us that our cosmological constraints, which are shown here by these red and blue dots from the Dark Energy Survey and Pantheon, are ruled out by lunar laser ranging constraints. And therefore, we cannot consider these models because they are not consistent with local solar system tests. However, models with larger exponents or magnitude of exponents can accommodate cosmological data and still be consistent with the lunar laser ranging constraints, such as the ones shown here. And so for the magnitude of m being equal to 4 or to 5, we can get cosmological constraints and local solar system constraints all being satisfied by this modified theory of gravity. In conclusion, the tracking solution was able to mimic dynamical dark energy with a phantom crossing showing up exactly as it does in the data that is favored by DESI. The lunar laser ranging bounds that we used impose tight constraints on our models, but some models with larger exponents, for example 4 or 5, can actually still remain highly viable while still offering a phenomenologically adequate framework to explain dynamical dark energy observations without ever breaking the solar system constraints, the local solar system constraints that modified theories of gravity often fall victims to. In the future, improvements concerning these LLR data are expected from better lunar laser radar reflectors of the next generation, expected to launch to the moon in around 2026, such as Moonlight. And I think the natural extension to our work really would be to relax this assumption about the tracking solution, so allowing the scalar field to move more freely around the potential and therefore expanding the parameter space, which could allow us, hypothetically, to fully recreate the dark energy effects, so fully recreate the dark energy itself instead of just dressing the cosmological constant with some dynamical behavior of its own. Thank you for listening.